All right. Is there anything anyone wants to bring up before we get into examples? Anything from the homework, from the reading, any talking points or sticking points or homework? Oh, no one? I have, as promised last time, I updated the encyclopedia. Let me make this bigger. This is the, whoa, stop. Okay. That's too big. There. Is that good size for you guys to view? You see that? Okay. So this is the encyclopedia, Carly.
Oh, I was just going to say, well, it's right going, but I can only see like your background. Like, do you have a web page pulled up?
Let me share. Yes, let me share. I thought it was sharing already. Can you see my screen now?
Yeah.
Okay. Thank you for letting me know.
Yeah, no problem.
Always stop me. Okay, so here's the encyclopedia. This is the pupil popularity example we were looking at in class last time. This is again, the example that Hawks begins, I think in chapter, is it 2? Yeah, he starts it in chapter 2. The students nested in class. Oh, my images are broken. Let me see if I can. I'll have to see why those are broken. So we were looking at I don't know why when I click there, it doesn't work. I gotta fix that too. Okay, so we talked about the ICC. And so the easiest way to do ICC other than hand is to use this performance package this was not on the encyclopedia last week. I've been editing it this week. So the easiest way is to say performance package, ICC function, all lowercase, and then put the name of the model in. Now to do the ICC, here's this big red box. ICC, you should only ever give that command the name of a null model with no predictors, and it should always be fit with REML. ICC is only accurate if it's a null model fit with REML. Okay. So I know there was a lot in the discussion board. How do you know when to do REML and how do you know when to do ML, which Hawks calls maximum likelihood FML. For, what is it? For full maximum likelihood versus restricted maximum likelihood. In R and every other book I've ever read, it's REML for restricted maximum likelihood and just ML for regular maximum likelihood. But again, he calls it FML. Now this is different from FIML, which is FIML, which is full information maximum likelihood. And that's what what M+ uses to deal with missing data for a structural equation model. Slightly different, it's mostly the same, but you'll see those different abbreviations in those different software or realms of models. Okay, so in generally speaking, with a null model, REML and ML will give you identical or near identical estimates, but sometimes they can differ in the random effects, the variance components. REML is better at doing random components, and that's why we use REML for the variance components that are used in ICC. So usually this is one of the first models you'll fit to your data, is a null model with REML to calculate the ICC. Null model with REML, no predictors, REML, and then do the ICC calculation. If it's a 2-level cross-sectional data set, the ICC tells you the % of variance in the outcome that is due to cluster variation. So in this case, our ICC was 0.365. So that translates to 36.5% of the variance in the outcome, our dependent variable population scores, is attributable to class variation, to differences between the level 2 units, which in social science, I will tell you that's big. Generally, in a lot of social sciences, you'll see your ICCs in the 10 to 20-ish range. There is no like important value, and like Neslick said in his video, there's no like cutoff, because the ICC tells you how the group averages differ. The averages differ, not the relationships between variables in groups. That would be a slope. This is how much the intercepts or the averages differ group to group.
That's what he says.
So I did have a notation question. And I'm sure I'm going to be asking about this notation stuff all semester, and it will seem really dumb. But like,
raise your hand if you still have notation equation or uncertainty. Yeah, see, Joe, you're not the only one. 2 hands for some people, even. Yeah.
Well, in 2 months, when I'm still asking, will definitely be bad. So on page 42 of our Hawks.
42.
So yep. Kind of write a typical. I mean, this. Figure equation 4.1, of course, it introduces the interaction there, with the z and the x times. And so a lot of those terms I'm understanding. The one I'm not now is, so the E, the last E is the individual residuals. The U is how much the like level 2s or the groups vary. So, and then those little y's are like pretty much the slope for those different variables. Why? Yeah. What's that one little u where they put it where all the little y's used to be? Why all of a sudden is there a u in this one instead of all the previous y's?
Okay, let me see if I can pull it up. Okay. So this is Hawk's equation 2.5, but it is very similar. So these y's here are really gammas. So let's call them gammas, but they look kind of like a y. You're right. So those gammas are like what we used to call a beta. They're the marginal or the average intercept and slopes. And here you can have a gamma for a level 1 predictor, which is an x, a level 2 predictor, which they use z, or an interaction, cross-level interaction. So this zx1 is a cross-level interaction between the first level 1 predictor at x1 and z, the level 2 predictor. And here we have a second cross-level interaction. This one's between the second level predictor, a second predictor at level 1 with the only predictor at level 2 in this case. We've got them listed in here. So those gammas here, the gammas are all fixed effects or marginal effects. Now this was a clarification on, I think I put it on one of the discussion boards. I think it was in the last discussion board about, maybe it was even this one. Let's see if I can find it. So we have this question that kind of came up last time. Variables can have fixed and the same variable can have a fixed effect and a random effect, kind of. So that kind of threw a lot of you for a loop last class when we had a variable having a fixed and a random coefficient. And this, I'm trying to find this link. Oh, and by the way, Alex found a really great explanation here, and she linked it. I almost linked this last week, and I decided not to overwhelm you. So if you don't want to look at it, that's fine, but this is a really good article about random versus fixed here, determining which you want. But that's not the one I'm looking for. So all this, I haven't read all this yet. Okay, it's not this discussion board. Maybe, let's see. Hawk's chapter 2. But it's in this one. Go back. Oh, I think it was there. Should have pulled this out so I had it ready. Okay, I can Google it right now. MLM, HLM, now this factor fixed. See if I can quickly.
While you're looking that up, can you,
Yeah.
Joe, can you repeat your question now that I have the book pulled up?
So do you see all the gammas that represent the coefficient, like the slope? There's the big gamma that's the intercept at first, and then there's a gamma with a level 1 variable, then there's a gamma with a level 2 variable, then there's a gamma with an interaction term between a level, but then all of a sudden the gamma turns into a U. And I mean, I was following the nice pattern with the gammas, and then all of a sudden I saw U.
Okay, yeah. So this website, the analysis factor, is a great website. They have a lot of great stuff on a lot of topics, multi-level modeling, including, I can't find it. I'll have to see if I can find it later, and I'll send out an announcement to kind of point you at it. But so this equation is very similar in that you have gammas, the intercept gamma, which is a fixed intercept, and then you have fixed slopes and cross-level interaction slopes. And then the U0, U that's by itself, is the random intercept. And when you have a U that's with a predictor, that's a random slope. So in the Hawkes equation 4.1 on the top of page 42, that U in front of the X variable is telling us that the X variable has a random slope in addition to a fixed slope. So it's that same idea is the variable X here is having a fixed effect and a random effect. So the gamma is showing the fixed effects and the U is showing the random effect.
Mm-hmm. Will there always, I know this is going back to what we were kind of just talking, will every random effect with a variable also have a fixed?
No. So one way, this is what I was trying to find the article. So we know about fixed effects. Fixed effects, whether we now call them gamma, they are just the same thing as what a beta used to be in simple regression. It's saying this is the overall effect of this variable in the population. The random effect, having a random slope, is saying that instead of just having one effect, the effect of that variable has an overall effect, and then it has an effect that's slightly different in each group. One way to think about it, and this analysis factor really well article that I was trying to find points it out, a random slope is really an interaction between a fixed effect and a grouping level.
Yep.
And that's how, and kind of the rule is if you have a fixed effect, it's fixed. If you have a level, it's a random effect. But if you have an interaction between a fixed effect and a grouping level, that's a random effect. So fixed interacting with fixed is still fixed, but fixed interacting with random is random, like the random overrides it. So going back to our pupil example, let's come down here a ways. Okay. So here, this M1 equation, we went from the null model with no predictors to this really first model that was really complicated. It had 3 predictors. In this case, gender is a level 1 predictor, so that's an X. We usually call it an X, so this would be like our X1. Extroversion is another level 1 predictor because gender and extroversion both apply to the individual students. So the gender and extroversion would be X variables. And this years variable doesn't apply to the individual students. It applies to the bigger cluster of students, the class. So that's like a C variable. So we have gamma, 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 gamma here. So these are all the fixed effects, fixed intercept, fixed slopes of level 1 variables and a level 2 variable. And then down here we have the U's. The U's are the random parts. So the U zeros, that is the random intercepts. And now we have a U in front of the gender variable and a U in front of the extroversion variable. So these are, in a way, interactions between the fixed effect gender and the clustering, between the fixed effect extroversion and clustering. That's what the U's are. The random slopes are interactions between a fixed factor, a fixed predictor, and grouping variable clusters. Now, how do you know whether you should have fixed or random? That is a question. And it's best if we can decide that based on theory, but if we don't have theory to guide us, then we can fit competing models and see which one fits better. So this first model, M1, Hawks fits the 3 fixed effects and 2 random effects. That's like as complicated as you can get without interactions between variables. And then he said, so here's, we go from the null model with no predictors down to here. See, these variables, sex, extroversion, and teacher experience, the variables that are outside the parentheses, those are the fixed factors. So those are the ones that would have a gamma, that U-ish gamma, the Greek gamma. The things that are here in the parentheses, these would be, it has the vertical bar class, so we're letting sex, the effect of sex, vary within classes, class to class, and extroversion vary between classes. And so this is, these sex and extroversion, because they're inside the parentheses, the formula would include a U in front of them. So variables out here would be fixed and have a gamma in front of them in the equation. Variables that are inside the parentheses would be random and would have a U in front of them instead of a gamma. And so sometimes we have variables being one place, sometimes they're the other place, sometimes they're both places. So here he went from nothing to pretty darn complicated. Now, the truth is probably somewhere in between. We're always trying to balance the complexity of real life with parsimony to be able to explain relationships with the power, the sample size we have at hand. So our final model that we're probably going to publish and say this is it is going to be somewhere in between the null with nothing in it and this full model with everything in it, fixed and random, as complicated as possible. So, but these are the 2 extremes he fits first. He calls this one model 0 and this one model 1. And then he goes ahead and he fits several models that are in between. So these models, they all have the same fixed effects. All 3 of the variables would have a gamma. But the difference is this one has 2 random effects. This one only has 1 random effect. And this one only has just random intercepts. And random intercepts, and then this would be random intercepts and slopes, and this would be random intercepts and 2 random slopes. Now, when we are comparing models that differ in terms of, they have the same fixed effects, but different random effects, this is what we want to use REML. So REML has, there's 3, let's see, I'm going to stop sharing this and we're going to make a little, like, I think I have it on there, but I'm going to, let's see, how do I get to share screen again? Come on, okay. I'm going to share the whiteboard. But if I pull it over to this screen and take you guys over here, pull this over there. My screen. Technology, it's going to be our friend, right? Get everyone's pictures. Okay, got everyone. Okay, here's this whiteboard. Okay, so this was the question. When do we use REML and when do we use regular ML? Especially because the results are going to be largely the same, right? This was a big question. So in general, we use REML when the focus.
Sarah?
Yeah.
Should we be able to see something?
Oh, you can't see it?
I see a white page.
Do you see a white page with some red writing coming on it?
No,
No writing?
no writing.
It almost kind of looks like we have like a cropped view of it because it's only just like the center rectangle of white and it's, you know, mostly like
Looks like a
black
sheet of paper.
bars.
Okay, can you see
Yeah.
the red line now?
No,
Mm-mm.
Do you see the red line now?
no.
Hmm. Okay, let me stop this share. Let me try it again. Share, whiteboard, share. Can you see it now?
Yeah, I see a red line.
I don't know why. Well, so now I've got a kind of a grid here, right?
Well, now it's widescreen. It looks very different.
But you can see my writing.
Yes.
I wrote REML on one side and ML on the other. We can see it now? Okay, so REML, thank you for letting me know. Focus of REML is, it does a REML does a better job with random components. ML does a better job with fixed components. Oh, but I don't want to shrink that. Okay. So we always want to fit our null model with REML to be able to calculate an ICC. And that's usually our very first step. So we usually fit the null model first, no predictors, using REML to calculate the ICC. Now this is the, let's see, I think it's chapter 4. Hawks lays out his approach, which is called a bottom-up approach for doing. Now, it's always best if you have theory. If you have theory, always go with that first. But if you have no theory about what should be included or not included, this is the analysis strategy Hawks starts with in chapter 4. So this is Hawks chapter 4, 4.1, actually, even more specific. So, and I have said this in an article before. We use the approach laid out by Hawks for building, model building. And I'll cite this textbook. I have done that in publications before. That is totally valid. So after we fit the null model with REML to do ICCs, then he says that's step 1. The intercept only model with REML to calculate the ICC. Then step 2, we add in fixed factors. So we refit the null model and then with ML, and then we fit it with fixed, we add to it fixed effects. This is not what we did in example of pupil because he was trying to illustrate something in chapter 2 or 3. But this is like the general progression we usually do. So these fixed effects can be level 1 or 2, or if we have it level 3. Now, if we're adding in fixed effects, those models need to be fit with ML because ML is better for assessing the significance of fixed effects. It does better with fixed effects estimation. So usually we start out with just a random intercepts model, unless we have theory to say otherwise, and we add in fixed effects. So that step 1 is the null model to get the ICC fit with REML. Step 2 is we change from REML, we swap over to doing ML, we refit that null model the same way but with ML, and then we add fixed effects predictors to it until we decide which ones are significant. Then step 3 is we bounce back and we take whatever best model we fit with ML with the fixed effects, and then we try adding random slopes. But if we're adding random slopes, we need to have those models fit with REML so we can assess better the random slopes. That's step 3. Oh, let's see. He breaks this into a couple he says, first do level 1 and then second do level 2. And then step 3 is to add in the randoms. So he says, first add level 1 predictors, decide which one of those are significant, then add level 2 predictors, see which one. So this should, I erased that and then I didn't do it right. All right. So level 1 is the null model to get ICC. Level 2, or step 2 is to fit level 1 factors. And then step 3 is to add in, let's see, let me make this clear. When I'm done with this, I will post this on Canvas, so you don't have to be like trying to memorize this. So step 2, we're gonna refit the null model and add in level 1 fixed effects. Then step 3, we're gonna add level 2 fixed effects to find out which ones are significant. And then step 4, we're gonna add in random slopes and find out which ones are significant. When we're doing, the focus is on random components to do an ICC or random slopes, those need to be fit with REML. If we're adding in fixed factors to see if they're significant, we need to use ML. Then we're going to switch back to using ML to look at cross-level fixed effects. So this is usually, unless we have theory is best to guide us, but lacking theory to go on, we this is the bottom up. We start with nothing, we add level 1 fixed effects, level 2 fixed effects, then random slopes, then cross-level interactions. And then the last step is, and does he say, let's see, 4, 5. He doesn't say it specifically, but you need to refit your final model with REML because it will be better that way. So the answer is, should you use REML or ML? And the answer is you have to use both depending on which step you're doing. And often we'll fit the same model with both of these. So we need to see an example of this, right? Okay, let me save this picture. So it is saved. And before I can forget, did it show my folder? Come on.
I have a quick question.
Yes.
When do we have to set a random intercept based on in table? I cannot find any information.
Null model is random intercepts. We always start with random intercepts. So this null model has random intercepts. And then we just add to that when we keep random intercepts in, unless there's a theoretical reason we should not have random intercepts, which we need to have examples. So if I push save, show and book. No, it's okay. It's saved now. Let me go back to sharing the website. So I'm going to share this one. And I want your pictures to be over on this computer so see everyone. Okay. Oh, it did put it here. All right, so here is this one. I'm going to put this in our Canvas. So if I go to Canvas, to our files, into the lectures folder. So I'm going to put this in. So it's in chapter 4. I am going to put that whiteboard snapshot in there. Okay, so that's in here. I should probably rename that. And we're going to rename this. Should I say whiteboard REML ML steps? Okay, so it's in Canvas for you. Okay. So I'm going to come down here to chapter 4 in the encyclopedia. This is an example that is not in your book. It's in a textbook, another multi-level modeling textbook. It's called Multi-Level Modeling in R, which sounded like a fabulous book, but I was so disappointed by this book. I tried to contact the authors, and the example data sets in there, they didn't have any code book for it. They couldn't even tell me who had gathered the data where or what the variables meant. It was all convoluted, and the textbook has so many mistakes in it. But this first example was fairly good. So in this data set, there are lots of levels. There's students and classes within schools, within states, but we're only going to look at just right now students being nested within school, just so we have a 2-level example. So you can read this data set in from their website. It has, again, this is students in schools or classrooms. We have the gender of the student, the age of the student, and we have a vocabulary score for each student and a reading score for each student. So these are all the level 1 variables because they apply to individual students, our smallest micro units. But those students are then clustered into classes, and we have a class level variable called class size. It's like how many students were in each class. So some classes are smaller and some are bigger. And then the classes are further nested in schools, and we have the schools enrollment and the schools SES, which is probably percent based on like something like percent of free and reduced school lunch and average property tax for the school zone or whatever. So the data set. So in this one, there are actually 9 regions that are divided into 16 cores or like school districts. And within each of those, there are a total of 160 schools. And within those 160 schools, there are 568 classes. And within the classes, there's a total of over 10,000 students, to give you some scope. So this level 1 is students that are nested in classes, which are then nested in schools, which are nested in school districts, which are then nested in region. So this is a very hierarchical data set. Those of you in education, this is common that you have tons of levels. Now we're going to simplify and only think of the 2 levels, students and classes. Here, what we are particularly interested about in this classroom is just the vocabulary score. Is that predictive of reading? What is the relationship between vocabulary and reading? Here, our dependent variable is going to be reading. Who was reading measured on? The school as a whole? The class as a whole? No, it was measured on the student, individual students. So our outcome is, our dependent variable is going to be this generalized education reading score, and our main predictor of interest is this vocabulary score. Now looking at this plot, do you see a relationship? Jill, you're kind of doing this. What do you mean? How would you describe it?
I mean, it looks somewhat positive and linear, but then it increases in variability as it gets higher.
Yeah, so but there looks like there might be something going on here, enough to pursue.
Absolutely.
Yeah. Okay, so this is just all the 10,000 students thrown on the same plot. I tried to do it with geom point and geom count, and it was just a black blob. So I moved to doing this stat hex bin. On the homework, I asked you to make basically a scatter plot, but it has a big sample size. So this could be some helpful code if you want to change it to hexagon heat map so that you can see better instead of just having black blobs. So here I have looked at, here are 4 of the classes, and I've done a regression line on each of these 4 classes. Is the association the same for each class? Somewhat, they're all kind of positive, but there might be a little bit of difference. So here I've done, each blue line is a regression for each class, ignoring the other classes, so 1 at a time. And then that dark red line is the average of all the regression lines. So the red line, its slope would be the gamma, the overall population average association relationship slope. Each blue line is how different, are all the blue lines exactly the same? No, U measures how different the slopes are for each class. So Joe or Joseph? I keep calling you Joe, but do you like Joey?
Joey.
Joey.
Whatever. I don't care.
You'll answer, okay. So the red line slope would be our gamma. The blue line slopes are all the U's. So the slope of vocabulary, we have an overall grand average slope, but then it does vary class to class. And so this is where a variable that we would probably want to at least investigate, that the GE vocab variable, that it would be outside the parentheses and inside the parentheses. And we would want to test if that helped the model fit better to have it both places. Now, how much class to class variability, if it's statistically or significant or not, we can't really judge that based on the plot. We need to actually fit the models. Okay, so here I've taken this spaghetti plot with all of the classes, this hairball, and I've split it out and separated it by faceting. Here I'm showing the schools on the lower half of the SES versus upper half, and then size of the school. The smallest the schools that had the smallest, the middle, and the largest as far as size. And if we look at that, do you see any relationship? Does it look like we should investigate the relationship, if the relationship between vocab and reading, is it consistent on SES and school size, or class size, or do you think that there might be a relationship? If you look at all 6 of the panels, can you see, are they all the same, or are there some differences? Visually, at least. Chung-Soo, you're nodding or shaking your head. What do you see?
They are totally different based on the SES and enrollment.
Yeah, if we look at the top row, we see a lot more variability, right? So that might be that we want to look at a random slope or a random effect of SES. Plotting it can help us know whether we want to have try variables to see if they have a fixed effect or a random effect, or potentially both. But again, we can compare the model fits to decide, does it help or is it insignificant? So here is kind of stepping through the data. So this is skipped. Oh, first is doing LM. We're going to skip the LM. We're going to go down here to multi-level modeling. Step 1, we're going to fit the null model with only intercepts. And when we do that, to do the ICC, we need REML, yes, to fit REML. But to compare it by adding fixed effects, we also need to fit it with ML. So it's usually best if just you start off fitting the null model, and we know this is the null model because we have no variables here. We're doing reading score with a fixed intercept and a random intercept for each school. So I'm going to do it. This first one is using ML. So notice the name. I said fit reading 0 ML because I'm fitting my model for the reading scores with no predictors by ML. And I know it's ML because I told it REML equals false. So the only other option with this is ML. And then I'm doing the exact same model, but with REML. Now, let's take a look at this. Now I put in a table, and here I put the code as screen reg, but to actually make this table in the background, it's doing invisible to you HTML reg so that it can make a pretty table. But here's my ordinary least squared model, my multi-level model, null model with ML, and my multi-level model with REML. Now, if you look at the fixed effects, the grand intercept, ML, REML, are they the same or different? Nearly the same on the fixed effects. Let's look down here on the variance components. What about the variance components? Are they the same or different? Pretty the same, right? So in a null model, ML and REML Usually is not going to make a ton of difference, but we need to do them both for the different purposes. I do want to point out the fixed effects comparing ordinary least squared to multi-level model. The beta of ordinary least squared and the gamma of multi-level model, that intercept, is it the same or different between the two versions?
Pretty similar.
Pretty similar. It's a little different in the second decimal place, but pretty similar. What about the standard errors in the parentheses?
Different, but also
different.
somewhat similar.
They are somewhat similar, but look at ordinary least squared. In ordinary least squared, where you ignore clustering, your standard error will be too small. And so the p-value ends up being too small as well. So you get more flashy results. Now in this case, both p-values get 3 stars. So it doesn't change the story, but sometimes it can. So this is what Hawks was talking about in chapter 1. If you disaggregate, ignoring clustering, your standard errors will likely be too small, which will inflate your type 1 error rate. Possibly. Okay, so when I do the ICC, which model am I going to tell ICC to use?
Remel.
Remel, no model. So here I give it. I did it by hand, but here. So I say the performance package ICC, the null model with Remel. Now, check out this ICC. Our last IC was 36.5%. This ICC is only 7. So this means 7% of the variance in reading scores is due to school differences. It's a smaller portion, but it still is probably an important portion, so we shouldn't outrule it. Plus, this is just saying that different class averages, the classes make it different on class averages. All the class averages are not the same. Okay, so step 1 was to fit the null model specifically with Remel, so we could do the ICC. Then what was step 2? We're going to add lower level explanatory fixed effects. And to do that, we need to use ML. Now I already refit the null model both ways above. So now I'm going to start adding in variables. So here I've added in vocab. That's my main variable. Now I've also, here I've done it with ML and I've also done it with Remel. So we can compare the two. So we've got a null model here and added a predictor. Now I'm comparing them both with ML because these two models, they both have just random intercepts, but the null model has no predictors and this second model on the right has added a fixed effect. Now to decide if that fixed effect is significant, we could do summary and look at the Wald test, but that's not reliable in all cases. So a better way is to compare the model fits. And we have at least 3 numbers to compare for model fit. The log likelihood with a likelihood ratio test, and then just visually compare the AICs and the BIC numbers. To do the likelihood ratio test, these models 0 and model 1 are nested because model 1 here is identical to model 0, adding in 1 variable. That makes it nested. If you take one model and add something to it without taking away, that's a nested set of models. And so the way to do a likelihood ratio test in R is to say the word ANOVA, for whatever reason, and then give it 2 model names. So here are my 2 models. What we've got, it says how many parameters. So the null model has 3 parameters: fixed intercept, random intercept, and residual variance. Now for the next model, to that I am also adding the fixed effects of vocabulary. So that makes it a 1 degree of freedom test, because the first null model has 3 parameters. The next model, I added 1 for 4. So that's a difference of 1. So 1 degree of freedom test. I take the log likelihoods, double them and make them positive, subtract them, that's my chi-squared value, and we can look up the p-value, and it's a 3-star p-value. How do we interpret a 3-star p-value on a likelihood ratio test? Anyone want to give it a go?
Is it that the models are significantly different from each other?
Models are different from each other, so which one's better?
50% would you
likely to get it right.
more complex model?
The more complex model fits better. Yeah.
Is it
So
because
when
of the deviance you're looking at that's less?
Yeah.
Okay.
Deviants are less, and they're statistically significantly less. If we look at let's look at the AIC. Which AIC is lower for this more complex model? BIC, which one's less for this more complex model? So you can look at AIC and BIC and see which one's smaller, but the likelihood ratio test compares the deviance, which will actually give you a p-value based on the chi-squared distribution.
Is the deviance value on its own interpretable at all, or no?
Not really, because it depends on the units of the outcome and the size of the sample and who's in your sample. If we were to redo this model, but only do it on and take out a school, the deviants are going to change because we'll have less students in there. So the number itself doesn't tell you. It's AIC and BIC and likelihood and deviance. The number values tell you nothing. It's when you compare them to another model that they're useful. R squared tells you something because it's always between 0 and 1. ICC is always between 0 and 1, so the number tells you something. AIC, BIC, log likelihood, deviance, alone, they don't tell you anything. They are only helpful comparing models one to the other. Because they're called relative model fit, not absolute model fit. Because they're only good for relating models to each other. So here I've done the plot of the variable. Okay, so here we're going to get into R squared type measures. Okay. R squared is a beautiful concept in ordinary least squared. What does an R squared tell you? Let's see, let me come up here. Let me get a model out for you. Okay, let's look at this model. This model right here, it says 1 IV, 1 independent variable. This is predicting reading score with just vocabulary score. Here's its R squared value, 0.29. What does that tell you?
So the percentage of variance that not explains that it's, what's the word I'm looking for?
Explained by or account. So
yeah, like account. Yeah.
so
You know what I'm saying. I can't use words, but yes, the percentage that of the model, or it explains, whatever.
It's 29% of the variance in the outcome is explained for by the variables that are in the model as predicted. So
yeah, that's what I was trying to say. Thank you.
Vocabulary scores alone explain 29% of the variance in reading scores, because readings are dependent variable. Yeah. So we don't need another model. 29% is a lot. We just know that 0.29, that's a pretty good number. That's almost a third. This is an absolute fit statistic because we don't need to compare it to another model to know how big 0.29 is. We have a frame of reference because we know it has to be between 0 and 1. When we go to multi-level models, R squareds are not So simple. So I'm going to go into this formula warehouse and down to this 1.5 proportion of variance explained. So there in Hawks covers this on pages 61 to 63. So this is part of the chapter you're supposed to be reading now, right? Chapter 4. So R squared you think would be easy. It's very easy for 1-level models, but it becomes very difficult to define in 2-level models. In general, here's some generalizations. We can use R squareds to compare models. And so the baseline model is usually the simpler model. Often that's the null model, but it doesn't have to be that. And we're going to compare it to a more complicated model. So usually when we say the R squared is 0.29, we are comparing the model with predictors back to the null model with no predictors. So by adding the variables in the model, we increase the percent of variance explained by 29%. We go from 0 to 29%. In general, we should only compare models as far as R squared that do not include any random effects. So they should only have fixed effects and a random intercept. They can have a random intercept, but they shouldn't have random slopes in them to do an R squared measure. Now, Snyder and Bosker, their book's over there. I won't take the time to grab it. They worked on R squared values. They were some of the early people to develop multi-level models formally. Well, Radenbush and Broerk, we've heard those names before. They were also working on the same type of mathematical problem with multi-level modeling, and they came up with different ways to calculate an R squared. And they have to do whether you ignore the random intercept or you include the random intercept in your calculation. So let me go back to our example. I have a pie chart. Okay, pi here. Oh, I thought I did the pi squared here. Not gonna come up there. Okay, we'll ignore that. So we've already seen that for a multi-level model, we break up the variance in random intercepts and fixed predictors. And so we get multiple, that's usually how an R squared is. It looks at the change in the residual variance. Residual variance isn't the only piece of variance anymore when we do a multi-level model. So notice these two formulas. Both of these formulas are trying to look at R squared, meaning proportion of variance explained at level 1. So both of these are for level 1. This one is for a random intercepts only model, and so is this one. Now Radenbush and Broerk, they made an approximate formula. Let's look at what the pieces are here. We've got it's how much the residual, the noise goes down. So you take the noise in the null or baseline model, the residual variance, and you subtract how much variance there is remaining with the predictors, and you divide it by what you started with. There's a problem with this formula in multi-level models. The residual variance can sometimes go up because the variance gets explained at other levels. So sometimes this formula ends up coming up with a negative R squared. What does a negative R squared means? If R squared is interpreted as proportion of variance explained, it doesn't make sense to be negative, right? We add variables. We don't explain more variance, we unexplain variance. That doesn't make any sense. The math gets complicated. So this formula although valid, can have problems. So Snyder and Bosker tried to address the problem of negative R squareds by slightly changing this formulation around. One of these is not better than the other. Now, Hawks in chapter 4, his equation 4.8 is the Radenbush and Rourke approximation. So it's an approximate R squared. It's not as simple as regular R squared. Now, we can also explain variance at level 2. And again, both of those two authorships have different versions of their formula. Now, the good news is you don't have to use these formulas, because guess what? There's a package for that has a function that will do it for you. I see some smiles. Aren't we glad? These formulas, what do you think when you see these formulas? Gag, right? Alejandro's giving the thumbs down. Yeah, we're going to let it compute it for us. So let's go back to our example. Okay, so we were adding in the independent variables, predictors at level 1 to get their fixed effect using ML. Here's a little note, if we only have level 1 predictors and random intercepts, if we have no random slopes and no higher level predictors, then your multi-level model will give you almost identical results to ANCOVA, provided you have no missing data. This is how ANCOVA came about. It's a simplification of a multi-level model. So ANCOVA is assuming that you only have random intercepts and you only have one level, predictors from one level. That's a little side note, might be interesting. Okay, so if we are adding a variable in, so I said in our little picture, after we fit the null model, then we're going to add fixed effects at level 1. So we add them in, but we need to know whether they're significant, and we can't use the good old Wald test. So instead we do a likelihood ratio test. We decide that yes, vocab is a significant predictor of reading level, a reading score. So that's that level. Now we want to get an R squared. How much variance does it explain? So we can do the formulas, but that good old performance package that gave us our ICC, you can say performance package R2 is for R squared, and then you give it the name of the model that has predictors in it. And look, it pops out your R squared. Now the R squared that's done here, which one are they doing? Snyder and Bosker or Radenbush and Rourke? It's not the same method that the book is using. So I wanted to show you again how you can figure this out in R. So here I'm in R. I'm going to slide this over. In my help menu, I'm going to come over here and type R2. And if I hit enter twice, it should bring up the help page. The other way is if you come into your console. So here's my console, and I'm going to type a question mark, and then I'm going to put the command performance package function R2 with no parentheses. So you put a question mark and then the package ;: function. No, just R squared. That will also bring up the help page. So let's peruse our help page so we know how to read this. Okay, so this R2 function in the performance package computes the model's R squared value. It can do, now this is the generic formula, it can do R squared, pseudo R squared, marginal, and adjusted R squareds, depending on what kind of model you give it. So this R squared function works for ordinary least squared models as well as generalized models like logistic regression and multi-level models. It works on Bayesian models. This is a really good overall function. So you give it the name of a model. Based on that model, it will give you a different kind of R squared. Now, if we give it a mixed model is mixed effects. This is what we're doing right now with the LMER function. It gives you what's called, I don't even know. I'm not even going to try to say his name. This is the kind of R squared it gives you. I can click on there and it will bring up the formula, the details, Look, here is a paper with a DOI number that you can click on to read the details about it. Look who is the first reference here. It's Hawks. It's an earlier version of this book. It's the 2010 second edition of this book that we're now in the third edition. Back then, he was the only author of the book. He hadn't brought his co-authors in yet. This is a good citation. So this is the method it's using to do R squared. Now, a lot of people debate what's the best R square formula to use because there are lots of different versions of it. This is generally my answer to most conversations or arguments. Pick one and use it. Just make sure you say which one you're using. So in your methods section, you would say that we're using this formulation of R squared. Be transparent so it could be reproduced. You don't have to get caught up on which one's better or worse, but make sure you say which one you're using. Okay, so R squared. So what is this? It gives us a conditional and a marginal. The conditional is the percent of variance. So this is 29.5. So 29.5% of the variance in reading scores is accounted for by the vocabulary score, but the conditional one excludes it. It's making the pot excluding the random intercepts. The marginal will either be the same or smaller because it's out of a pot that includes the random intercepts. So it has to do with which formula you're using. Now, 29.5%, that's almost 30%. So almost 30% of the variance in reading scores is accounted for by school membership and vocabulary scores. That's how you read the conditional. The marginal is 27.6% of the variance is attributable directly to vocabulary scores after accounting for school-to-school variability. These numbers will be slightly different, but they both are in the same ballpark. They're both close to the same number, usually. So here's the formulas, using their formulas by hand. Okay, so that's how you do a single predictor. But usually, we don't just add one predictor at a time, we'll add a block of predictors. So when we add vocabulary, that's a student score. We can also add the student's age. That's also a level 1 predictor. So this is looking at the fixed effects of vocab and age. That's what I'm calling model 2. What did I do different in model 3? Alejandro, what's that?
An interaction.
An interaction. So in model 2, I have the main effects of vocab and age, and then in model 3, I let them moderate each other. Is the moderation significant? I don't know yet. Well, let's look at the model. So here's with vocab only. This model just has vocab. Then I add in age, and then I add in the interaction. So I'm building up my model one step at a time. You don't have to do one variable at a time. I'm just showing how you could do it. Now, what happens to the residual variance? Look at the residual variance at the bottom. Does the residual variance get smaller? Does it get a lot smaller? Now, in this TechReg table, we get walled stars. So let's look at the walled stars. These are doing walled p-values. In model 1, is vocabulary significant? Yes, it gets 3 stars right here, 3 stars. These parentheses values are not the p-values. Those are the standard errors. So we're just looking at the stars. So vocab is significant when it's alone. What about in this middle model when I have vocab and age? Are those 2 main effects significant? Joey's giving us a sum up. Yeah. Vocab still has 3 stars and age gets a star. Now the question, do they moderate each other? So now look at the moderation. Is that significant? Yes. So we've compared these models. Which one should we keep? Which one's the best out of these three? Model 1, 2, or 3 is the most complex? What? Show me fingers. Model 1 is vocab only, 2 is both main effects, 3 includes the interaction. Fingers? 1's best? Is this first one best? How do we decide at which model's best? 1? I see some 1s.
Would we not have to do the log likelihood ratio test again, or?
Should we do it? We should do a log likelihood ratio test. We should. One way is if, as we're adding things to this model, are the things we add significant? If the answer is yes, then they should be in your model. That's one thing, but that's based on the walled tests, which are kind of sketchy. So a better way is, like Carly said, we should do likelihood ratio test to compare 1 to 2 and then 2 to 3. Let's look at our AIC though. As we add things to the model, make it more complex, as it gets more complex, does AIC still go down? AIC does go down. Let's see, we get 43,132, 43,128, that's smaller. And going over here, yeah, that's even smaller. What about BIC? 43,161, uh-oh, what happens with BIC? Which one's smallest? According to AIC, what's the best model? 3. According to BIC, what's the best model? 1. According to the walled tests, which one's the best model? 3, because it has all stars. So really, we should do the likelihood ratio test. Now, I've shown you before you can do ANOVA and give it 2 model names, but you know, here, we can give it 3 model names. And it still works. Notice it has all 3 models in it. Just vocab, vocab plus age, and then vocab asterisk age. Now, the way it does is it does it stepwise down the table. So these first 2 lines, so there's model 1 that has just vocab. And then our first p-value is when we go from 1 to 2, we have vocab in both of them, but when we add age, does it make the model fit better? Yes. Okay, now let's look at this last line. When we add the interaction, does it fit better? Yes. So according to the likelihood ratio test, what's the best model out of 1, 2, and 3? 3. So walled tests say use 3. Likelihood ratio says go with 3. AIC says go with 3. BIC says, yeah, stick with 1. How do you make your choice?
Best 2 out of 3.
2 out of 3. Here's one thing. BIC is usually too strict, so you can usually ignore the BIC. If you have conflicting, the likelihood ratio test should be weighted the most. So the likelihood ratio test, if you have AIC, BIC, likelihood ratio test, and walled test, the likelihood ratio should be trusted the most in multi-level modeling.
Could we use a Lagrange multiplier instead, or is that less helpful?
The Lagrange multiplier, I've not seen that done at all in multi-level modeling. Not that I'm not saying that it couldn't be done or it doesn't have a place, that's just generally not done. Okay.
I have a question.
Yeah.
Are those log-like values the same here as they are in the other one?
You mean this column right here?
Yeah.
These are the same numbers that are log likelihoods there.
Okay.
Yeah.
And
And
then
the AIC should be, all 3 of those are the same down here.
and then this is just telling us that they're significantly different from each other.
Yes. It shows AIC and BIC. AIC and BIC, you can't do p-value tests between. Likelihood ratio test, you can p-value check between. But to do it, you have to do this ANOVA command, which is not an ANOVA model. It's confusing. Okay. All right, so we can look at the interaction, but we're not going to. So step 1 was the null model to get the ICC. Step 2 is to add the lowest level predictors, and they can interact with each other potentially. What's the next step? Step 3, after we've added the lowest level predictors?
Second level predictors.
Second level predictors. In this case, let's go for it. Okay, so now we're going to add higher level explanatory variables. They're fixed effects. So we've already decided we need vocab and age to interact. At level 2, we have school enrollment. S, enrollment, means school enrollment. So how big the school is. And we're making it a fixed effect. So this is now model 4. We're taking our best model so far, which was 3, model number 3, and we're adding another variable to it. Okay, so here's my null model. Here's with level 1 predictors only. We decided this was our best model with the vocab, age, and their interaction. Now we're adding school enrollment. Look at school enrollment. What do you think based on the beta? What's the beta? Or the gamma? What's the gamma for school enrollment? Pretty tiny. What about the Wald test? How many stars does that estimate get? No stars. So the Wald tests probably don't need it. Okay, let's look at AIC. So far we have this level 1 model. Now what happens to AIC when we add in school enrollment? Did AIC get better? No. Does BIC get better? No. So let's do the likelihood ratio test. But even before we do the likelihood ratio test, do you think that school enrollment is significant? Not looking good. No Wald stars, and it makes AIC and BIC worse. So let's do the likelihood ratio test. Here we go. What does it look like? That more complex model adding school enrollment is not worth it. So we tried adding a level 2 predictor, but we're gonna not keep it. So far, what's our best model? 1 null model, 1, 2, 3, or now this new model 4. 3. We tried a level 2 predictor, but we're saying not significant, we're dropping it back out. So far, now we're gonna, after we add level 1 predictors, fixed effects, level 2 predictors, fixed effects, if we have some of both of those, we could look at cross-level interactions. We don't have, since we don't have a level 2 variable, because we said it's not significant, then we can't look at a cross-level interaction because there's nothing, no predictors at level 2. So now we're gonna go and we're gonna look at random intercepts, or random slopes. We've always had a random intercept at this point. Now, model 3 is our best so far, but if we look at our model 3, where is it? Which estimation method did we use? ML or REML?
ML.
ML. Why were we using ML up here?
Because we're looking at fixed effects.
Because we were comparing models that differed by adding in fixed effects. Now we're going to add in random effects. So instead of ML, we need to use what for random effects? REML. Okay, so coming down here, I need to rerun this model 3 that we already said was our best model, but now we're going to rerun it. Instead with ML, we're going to switch it to REML. So look at it says model 3 still. We have the interaction between vocab and age, but only random intercepts. But now I have changed it to REML equals true. And this is so I can compare it to the model with only random intercepts for school. Intercepts varying by school to random intercepts and slopes. So this formula has only random intercepts because there's only a number 1 in the parentheses in front of the vertical bar school. This model 5, I'm just giving it the next number up, Now I'm adding the word vocab, vertical bar school. Now why vocab? Because that's my main variable of interest. When we looked at the plot way back up here, here's the school. Where's my spaghetti plot? Oh, it switched me to a different. This one. We see there is a relationship between vocabulary and reading. That's this red line. Our estimate would be this slope of the red line, but we can see in our plot that there is school to school variability in that slope. So the way you add in the potential to have school to school variability in the slope for vocab is to put vocab inside the parentheses, and that's what we're going to test now. Okay. Right here. Am I in the right? Model 5. Okay, it's right here. Yeah. Yeah, so I add that in. Now, I fit the two models. Now, notice what I had to do. This model failed to converge. So I had to try some optimizers. And I went to that link that I gave you last time, and I just tried all the ones that were there till I found one that worked. If it takes several times, you might be thinking maybe this model is just too complex for the data at hand. But if it converges with one of the optimizers, we go with it. What do we do if it fails to converge?
Make the model less complicated.
What do we do with the output that comes after the fail to converge error message?
Don't look at it.
Ignore it.
No, look at it. Somebody remembered. Yay. Don't look at it. Get it to converge or simplify your model, but don't use that failed convergence output. Okay. All right. So let's compare these models. So these models have the same fixed effects. Let's look. The random intercepts and the random intercepts and slope. So the top part of that table, the fixed effects, the gammas, did they change very much? They're pretty much the same. But let's look at the bottom of the table for the variance components. Have they changed? We went from only having school to school intercepts and residual variance. We've added in the random slope of vocabulary within school and then the covariance between random intercepts and slopes. So to decide if it's worth adding that complication in, we do a likelihood ratio test with the word ANOVA. But like I said last time, if these two models were fit with REML, we have to say, don't go back to ML, refit equals false. All right, what does this look like? Are the random slopes significant? Yes. So model 3 had random intercepts. Model 5 adds in the random slopes, and this p-value with 3 blinking stars means the more complicated model is worth it. So even though I had to do all this optimizer crap up here, it's worth it. Okay. So our best model so far is model 5. Now, usually when we get our final model, we would refit it with REML, but this has already been fit with REML, so we can look at the interaction. Now, I'm going to go in here and I'm going to add simpler code. This used to be the only way I knew how to do the interactions because the interaction package hadn't come about, but here's the interaction. What does it look like we got going on here? What's the role of vocab and reading? What's the relationship? How would you describe the relationship between vocab and reading?
The better vocab that somebody has, the better they are at reading.
Yes, Perfect. It's a positive association. Higher vocab goes with higher reading, lower vocab goes with lower reading. But that is moderated by age, such that, let's look at the red line is for younger kids, 7-year-olds. What does this look like for 7-year-olds? Compared to the blue line is for older 11-year-olds. It moderates it so that that relationship of vocab connecting to reading, that is more steep for the older kids and less steep for the younger kids, which might make sense because younger kids, their reading has less vocabulary in it, and as you grow older, you rely more on a diverse vocabulary to understand things you're reading. I don't know. Okay. I'm gonna stop this example here. Yeah, we're about out of time. How does this class fly? We didn't even have a break. You guys need to tell me to take a break. I get too excited. I was on a roll. Okay. I think that's where I want to stop with this example. The next part of this example talks about centering and rescaling variables. I'm going to hold off on that till next class time. All this code again is on the website, so you can cannibalize this code for your homework. Please refer to it. It's there for you. I do it all the time. Like every week I come back and copy and paste code off here. Okay, questions. We got 6 minutes till we got to sign off. With this example or any of these other examples or concepts.
Here's a simple one. Will you scroll back up to the table that showed the, I think it was the very first 3 where you just had vocab, reading, and interaction. The first time you did the interaction term.
Haha, there.
So just a little, I guess I'm just trying to still organize the cross columns and rows. So where I see the GE vocab row, I'm noticing the first with only vocab, it's significant, 3 stars. And then over there with both main effects, it's 3 stars significant. And then with the interaction term, it just has a negative coefficient with no significance. Is that saying that it's not, doesn't have an interaction with what? With its set, like?
Joey, I'm so glad you brought this up. So we see that in this middle model, we see that vocab is significant and its age is significant. But when we add their interaction, what happened to the significance of vocab? The significant vanished, right? That's what you're struggling with? It doesn't vanish. The significance of vocab transfers from being a main effect over the significance has been sucked in from the main effect of vocab has been sucked in to be significant in the interaction. So in all regression, if you have a variable by itself that's significant in one model and you knew another model and it's interacting with something else, you only look at the significance of the interaction. You no longer look at the significance of the main effects. The reason is that significance will transfer because of, one word for it is, structural multicollinearity. The main effect of vocab is correlated with the interaction with vocab, and that's why the significance transfers over out of the main effect and gets sucked into the interaction.
Okay. Yeah, that does make sense. I see it there now where it's sucked in there. Okay. Thank you. Yep, that's perfect.
Third model, when we have vocab and age interacting, we only looked at the significance of the interaction. We now ignore the significance of the main effects for this model. That's an important concept that's often missed in ANOVA and regression in one level. And now that we're going to 2 levels, it's still a fact.
Well, and that's why you have to add them piece by piece. You can't just throw them all in there and see which ones work.
Now, I could have skipped this model 1. You don't have to add the variables one at a time, but it is often helpful to add them in as only main effects and then add additional interactions. You don't have to add the main effects one at a time. Now you can add the block of main effects and to that then add an interaction, but the interaction should be added after the main effects. Yeah. Unless theory says otherwise. Theory should always trump any of these steps. Okay. So you guys are working on the first clustering part A assignment. It has you fit a null model and calculate an ICC. The next homework assignment is going to have you take that same data set and do what we just went over in this example. Add level 1 predictors and interactions, level 2 predictors. I think there's only one. Then add random slopes. And each time you add something, you check if it helps the model fit better. And if it doesn't, you throw it out. So you try adding things. It doesn't mean you will keep those things in. And then when you arrive at the final model, you make a table and make a plot. So that's the next assignment that's coming up down the line. So next week we will continue, I think on Tuesday, doing centering. And then we're going to start switching gears a little bit to longitudinal designs. Same math, but instead of people being the lowest level, people are the upper level and their observations on the same person are at the lowest level. Okay, our time is up, so you're welcome to log off, but I will hang out for a few minutes if you have other questions.
Thank you, Sarah.
Sarah, are you planning on doing any office hours?
Yes, let's set that up right now.
Okay.
Okay, I'm going to take my schedule. Okay, so I could do office hours early tomorrow, or I think no one probably wants to do them on Saturday, so I'm not even going to propose that. Tomorrow's bad for me. The assignment's due on Tuesday, so we could do Monday. What works good for you guys?
Does Sunday or Monday work for you so that like we have time to work on it and see what questions come up?
I'm going to say no on Sunday, but Monday definitely. Now, there was someone in the class that already tried the assignment and they were having really big issues right off the bat. They sent me an email. We set up a Zoom time. Within 45 minutes, they had the whole assignment done. So just because we don't have office hours doesn't mean you can't email me and we could set something up. But I don't want to set Sunday office hours, but I could do tomorrow early morning, or I can definitely do Monday. What time?
I could do Monday after 5.
Monday evening?
Yeah.
Anytime Monday is fine for me.
Okay, do we want to do 5 o'clock or do we want to go later on Monday?
5 would be good.
5? Okay, let's say Monday at 5.
Okay, thank you.
I'll send an announcement. We'll do 5 to 6:30 to give ample time. But again, if you're stuck, don't bang your head against the wall. Send me an email and either explain it in the email and I can explain it back, or say this is a time that works for me, and then we can set up a time to jump on Zoom for 10 minutes, 40 minutes, whatever it takes.
Thank you.
Okay.
Thank you.
Welcome.
Thanks, Sarah.
I have a really quick question about this assignment. Can I share my screen?
Yep, I'll just push stop on mine. Okay.
Can you see my screen.
Mhm.
I went through the most of the assignment, but
Mhm.
I have a question about. I wrote the table using furniture, but school
Yeah, but
is
school is, yeah, so there's two problems going on here. One is the output type, and that's why it looks weird. And the second one is that school is an identifier variable, and so each school has its own 4-digit number. You don't want that in the descriptive table. So can you pull up your R? If you can
Yes.
share your R screen, I can show you how to fix it. So you'll have to stop the PDF share, yep, and then share R. There we go, here it comes. Okay, so okay,
Yes,
here.
I think this
Okay,
part.
so you'll want to take out the school. Yeah, take out that whole school equals and yep, and then the comma 2. Yep, and delete. Yeah. And you can leave that empty space or you can move the next line up. It doesn't matter. Now just do that much. Run that. And that should get out all those school IDs. It's their ID numbers, which the school is either public or Catholic. That's why you see all those zeros. But you don't want that to be in your descriptive table. Okay, this looks better.
Just delete the school.
Yeah. Now to have it look better when you knit it on line 156, you'll want to take out that pound.
Okay.
Yeah. And then when you knit it, it will look better. It will look ugly here, but it will look better in the PDF.
Oh, okay, I see. Okay, thank you.
Okay.
Bye.
That'll help me too. So, quick, I had one quick, just conceptual question.
Mm-hmm.
Still trying to wrap my head. So, with fixed and random variables and effects, right now, for some reason, I've drawn the conclusion like level 1 variables, like gender, let's say student IQ, something like that, could always be both a fixed and a random, and is always, but level 2, say something like teacher experience in a classroom, could only be fixed in that case.
With only 2 levels, yes.
Level 2, level 1, level 2, thing like that?
What you're saying is correct when you only have 2 levels. Now there is another example that we haven't gone over yet that has 3 levels. It's this, we skipped it right here, the 3-level nurses study.
Okay.
When you have 3 levels, you can have random slopes for variables at all but the top level. Variables at the top level can never have random slopes.
I was wondering that. Okay, yeah. So it's pretty much, I mean, so that is like, I could follow that rule. I mean, the lowest level is always gonna, those variables are always gonna be random and fixed.
No, they're always could be tried to see if they have significant fixed and
if it improves the model, I see.
Yes.
But they don't, I see. But if, okay, they could be, yes, that makes sense. And
you can investigate that, but it's not always, just because you can write the formula that way doesn't mean that A, they will be statistically significant, or B, if you add too many things in, it can max out your sample size. So usually we only do 1 or maybe 2, never really more than 3 random slopes, because it's the random slopes suck up a lot more power and sample size than fixed effects do.
okay.
Now, people argue all the time whether when it's appropriate to because sometimes like a random slope might be significant, but it barely changes the model fit and it doesn't really change anything else. So do we really need to have it in there? Or it's more parsimonious to leave it out and we get the same story. People argue about that all the time. Does it really need to be in there or not in every case?
Yeah.
The key is go with it. Decide on which way you're going to do. Be transparent and reproducible about it. Be obvious in what you did or didn't do.
Yeah,
People
that really,
whether it's right.
yeah, some things are really starting to click. And so this is making a lot more sense. So but I'm just foreseeing in the future, good Lord, like that one example, what if you had, that one where you had like 6 levels? How are you trying to decide, like, you can't go through that process we just did like for days.
No, nor should you. That's called p-hacking. So usually we simplify down to 2 or 3 levels. Theoretically, you could model all 8 levels, but you have to have a good number. So if you've got to have, say, 10 regions, then you got to have 10 school districts in each region and then 10 schools with it. I mean, the sample size and the complexity just like blows up. And so for that reason, we usually only will model 2 or 3 of the levels. And so you have to have a good number of units at that level. And it also has to be conceptual that there is variance between them. So maybe it's beyond the scope of a study. And in this one that we just looked at, we know that there's school-to-school variability. Is there region-to-region variability? Maybe, but if we're talking about kids' vocab and reading, there's a lot of school-to-school variability. The region-to-region variability is probably fairly negligible after we account for school-to-school variability. So again, it's this balance of complexity of the real world and parsimony to have a testable hypothesis with the data we can access.
That's good to give me a vision though, because like in my mind, I was like, how are we gonna do this when we have 9 nested things? Because I didn't know like we go to 2 or 3 and that's kind of like what you do. Okay.
Yeah.
Like, oh Lord. Okay, cool. Well, that makes a lot of sense. Awesome. Thanks so much.
Okay. All right. We'll see you maybe Monday, but probably Tuesday.
Okay.
All right. Okay. Bye.